This is Himabindu from the Department of CSIT. So today in this video I would like to explain about the problem solving on regular grammars. So we already discussed about the regular languages and regular grammar. Now we will discuss about the regular grammar types and how we will design, how we will convert the given grammar into a finite automata and finite automata into a regular grammar. So here in this video, so coming to the introduction of regular grammar, so we already discussed the grammar which is having the four tuple representation. So in this four tuple representation, G is nothing but a grammar. So G is nothing but a grammar and V is nothing but non-terminal. So a set of variables or non-terminal symbols. So here V is nothing but a set of variables. We will represent these variables with the capital letters. Capital letters. And T is nothing but the terminal symbol, so we will represent it with the small letters. And S is the start symbol and P is the production rule. So here production rules which are nothing but we have a left hand side and right hand side. There are conditions. Based on the conditions we will follow, we will have the languages, we will have the grammar. So here now we are discussing about the regular grammar. So regular grammars are which type, in the sense type 3 grammars. So this type 3 grammars are having left hand side only single non-terminal and right hand side it is a combination of terminal and non-terminal combination. And the production rule has been of the form. So the production rule, which is having this kind of alpha tends to beta. So alpha is nothing but it is a single left hand side, it is a single non-terminal value. So non-terminal values which are represented with the capital letters. So capital letters, suppose we will take S is the starting symbol. So we will take it as a V. V is nothing but non-terminal. So it tends to beta. So beta is nothing but it is a combination of terminal and non-terminal. So beta is nothing but terminal and non-terminal. So this is one type of example. And also S tends to terminal is also a production rule. So these are the production rules for the regular grammar. So regular grammar which is having the left hand side only a single non-terminal. So single non-terminals which are represented with the capital letters. So this is the production rule what we are having for the fourth tuple. So grammar which contains the values like V, T as P. V is nothing but a set of non-terminals which are represented with the capital letters and T is the terminals which are represented with the small letters. So what are these terminals are nothing but input values or input symbols. We can say that alphabet, so sigma. So what we are taking as a alphabet in the regular language, those are represented with the terminal symbols. And next one, this is the starting state. So as in the finite automata, we are starting with the Q naught, like that. Here also we need to start with the one start symbol. So that start symbol here we are representing with the S. And P are the production. So here the P is nothing but alpha tends to beta. The P is in the form of alpha tends to beta. So here alpha is nothing but it is a non-terminal value and beta which is a combination of terminal and non-terminal value. And here is an example of the grammar. So grammar contains a four tuple. So in that one V is nothing but capital letters which are represented with the capital letters. So these are the non-terminal values. And next T is the nothing but input symbols. So input symbols A comma B. And S is the starting state. So in this one, which one is the starting state? We need to starting symbol which we need to start with the production, which equation is first started. And here these are the production rules. So here production rules are S tends to AB and A tends to A and B tends to B. So these are all, we discussed on terminal and non-terminal combination, but terminal and also have non-terminal and non-terminal combination also is accepted in the right hand side. So this is about the example of grammar. So grammar which contains a four tuple V, T, S, P. So V is nothing but non-terminal values which are represented with the capital letters, and T is the terminal value which is represented in the small letters, and S is the start symbol, and these are the production rules. So here this is about the regular grammar. So here, and coming to the regular grammar in the Chomsky hierarchy. So we already discussed about the Chomsky hierarchy in the Turing mission. So Turing missions which are of which type of grammars we are going to use for the construction of Turing mission. So here in the Turing mission we constructed with the grammars type 0 grammars. So here like that here in the regular grammar, so which are of the type 0. So type 3 is the regular grammar. So where type 3 is the regular grammar. So here, while coming to the Chomsky hierarchy, regular grammar. So we have types of regular grammar, and next context free grammar, and context sensitive grammar, and recursive enumerable grammar or unrestricted grammar. We can write unrestricted grammar. Unrestricted grammar. So here the type, this one is type 3, and CFG is a type 2, and this one is type 1, and this one is type 0. So here these are the four types of grammars we have in this Chomsky hierarchy. So which type of grammar is a regular grammar is nothing but type 3 grammar is a regular grammar. So here the type 3 grammar is a regular grammar which is a subset of CFG context free grammar, and which is a subset of CSG context sensitive grammar, and unrestricted grammar, subset of unrestricted grammar. So they have a single non-terminal symbol on the left hand side. So these are the grammars, regular grammars, which are having the conditions like left hand side. So left hand side tends to right hand side. This is the production rule. So in this production rule, left hand side only single non-terminal which leads to the combination of two non-terminals or single terminal, single non-terminal, and so these are all possible production rules with the regular grammar. So here they have a single non-terminal symbols on the left hand side and the single terminal on the right hand side, or a single terminal followed by non-terminals. So these are all possibilities of the production rules for the regular grammar. And this grammar accepts and generates the regular languages. So this regular grammar will accept and generate the regular languages. And all the productions should be in the form of, so the productions are of the examples. So here the single non-terminal which is representing terminal with the combination of terminal. So here X is the terminal. So and B is non-terminal is capital B, and here also it is a combination of only terminal, and it is a combination of, here in the third production rule, it is a combination of non-terminal and terminal. So here non-terminal is capital B and terminal is X. So like this we can form the productions for the regular grammar. And the one condition we need to note, so left hand side we have only a single value, single non-terminal value, only non-terminals. Terminal we can't represent in the production rule in the left hand side. And here is the condition we need to know. for the regular grammar. And next, where capital A, B or the V, so V is this A and B, this A comma B which are belongs to the capital V, so that is nothing but a set of non-terminal, set of variables we can represent. And x tends to x belongs to terminals. So here the terminal, so it will be represented multiple times. So like xxs like that. And the string of the terminals. So here the string of the terminals which are represented, that is nothing but t we will represent with the string of the terminals. So these are all the regular grammars which are in the type, which are in the Chomsky hierarchy. So Chomsky hierarchy, which is having the position like type 3 grammars, are represented with the regular grammar. And types of regular grammar. So how many types of regular grammars we have? So these types of regular grammar which are divided into two parts. Two types. One is left linear grammar and right linear grammar. So we have two types of grammars. One is left linear grammar and right linear grammar. So left linear grammar we will represent it with the LLG, left linear grammar. A grammar is said to be left linear if all the productions are of the form. So here, if you observe, the left hand side is all we have a single value, so there is a no problem with that one. And right hand side, when coming to the left linear grammar, we have first non-terminal which is followed by the terminal here. So which is followed by the terminal. So here capital B is the terminal, so V is nothing but capital is the non-terminal and T is nothing but terminal. So here non-terminal which is followed by terminal. So non-terminal which is followed by terminal with for the LLG, left linear grammar. So the terminal which is non-terminal which is followed by the terminal. And here one more A tends to X. So here A tends to X is nothing but X is a terminal value. So here the terminal value, single terminal is also a left linear grammar. And coming to, and here we A comma B which are belongs to the non-terminals, and X tends to X belongs to the T star. So T star, that is a string of terminals. So here these are the values we already discussed. And here coming to right linear grammar. So the right linear grammar which is right side. So right side we have to write the non-terminal values. Here in the left linear grammar, first we written terminal variables, then we written the terminals. Here, but here is the different, like we need to write first the terminal and then we need to write the variable. So here the non-terminal which is followed by first terminal and non-terminal, and also non-terminal which is also representing the T is also accepted as a right linear grammar. So here A comma B, with these are all the variables, and T is the X is the terminal. So here this two types of regular grammars we have. One is left linear grammar and right linear grammar. So we can convert one grammar into another grammar. So here we can convert the left linear grammar into a right linear grammar and right linear grammar into a left linear grammar. So there is further one we will upload coming videos. And here a conversion of a regular grammar to a finite automata. So here we already discussed the equivalence of regular grammar to a finite automata. So whenever we have an input like a finite automata, or whenever we have a input as a regular grammar, we need to convert it to a finite automata, the diagrammatic representation of the grammar. So the input is grammar, and now we will convert it to a finite automata. for that one, first we need to compare those two definitions. So we have the grammar, we have definition, and finite automata, we have the definition. So for both definition, we have the values. We need to compare both both the values, and then we will draw the transition. We will draw the transition diagram according to the production rules. So here we have the grammar, which is having the 4 tuple representation, and FA, finite automata, which is having definition like a 5 tuple. So here we have the input value is in the form of production rules. So production rules, and we need to convert it to a transition. So that is the point we need to note down. So when we give the productions, we need to convert it to a transitions. So whenever we have given a production rules, and we need to convert it to a transition. So here for this one, first we need to compare the values here first. So when coming to the finite automata, we need to finite automata. So first input is production rule. So the production rules which are having the VSTP production rules, and here these production rules which are going to be converted into a transition. So transitions which are having initial state, final state, and delta, and we need the sigma values, and sigma, and so alpha, sigma, and final state. So initial state, and Q. Q is nothing but how many states are required to construct the finite automata. So we need to convert this to a finite automata. And here first this Q, which is belongs to the V. So we have a capital letters, those are represented with the variables. So those variables are named as a finite set of states we here. So that's why Q is equal to V. So Q is nothing but a finite set of variables, and V is nothing but a variable. So here we need to compare both. This Q is equal to V, and now sigma is equal to T. Whatever the string we are having for the in the production rules, so those values are represented with the alpha, sigma. So sigma is nothing but the terminals, and the Q naught is the starting symbol. So here initially we have one, we need one initial state. So here also in the grammar we have starting symbol. So we need to equalize these two, and delta is equal to P. So delta is nothing but a transition. So here this is the important thing. We need to convert the production rules into a transition. So here when we choose the production rule now, then we will convert that into a transition. How we will see? And here a finite state F is equal to QF. QF is nothing but a finite state, final state. And next Q is equal to V union QF. So here Q is nothing but first what we need to write. So here V. So V already we have some let's take an example, some variables union. So Q is nothing but variables union a final state. So based on the production rules, we will have additional final state, so that we need to add that to a Q. So that means, so here initially we have this kind of states. After reading all the productions, we found some final state. So this also included in the Q. So this is nothing but Q, V is equalizing with the V. And next, if epsilon belongs to language. So if epsilon belongs to language, So in the language, epsilon is a input string. So first what we need to do, so epsilon is also, say f belongs to, so final state f belongs to qf with the s. So s is having the self state, that is having the epsilon symbol, and we need to represent with the diagram. So this is about the comparison, and then we will take one example and we will convert the production rules into a transition. So we will take an example of, so here production rules we need to take. And first we need to write the production rule, then we need to convert it to a transition. So here we will write s tends to, we will take a right linear grammar. So a, and also a tends to a. So these are the production rules example, and now we will convert this production rule to a transition. So transition is representing with a delta. So delta of, so current state we need to take. So current state is S, and when we are giving A as an input, it is reaching A state. So this production rule, how we written in the transition. So this S is the current state, and in terminal, which is followed by the non-terminal, and A is, so here A, for A input, it is reaching the A state. And for this production, so S tends to A, comma, input A. So it is, there is no non-terminal. So how we will represent with this one here? Instead of this A, QF we will take. So QF is the final state. So when we have a single terminal value, so that represent it is reaching the final state. So that's why we need to write like this. So state is not mentioned here. We need to write the final state. So this is how we need to convert the production rules into a transition. And we will discuss more with the examples how we will convert the regular grammar into a transition. And here is the example 1. So here we have taken the grammar for the regular expression like a plus b, a into a plus b. So here which says that the string is going to be either it is starting with a, or there is no condition like either it starts with a or b and it is ends with a or b, and in between there is nothing. So here this kind of regular expression, if you observe ab plus all the possibilities ba and bb, aa. So these are the equations for this. For this regular expression, we need to write the regular grammar. So regular grammar which have, so first we need to start with the S state. And so this regular expression says that the string is going to be start with A or B. So that says that A, if you take A as a input value, it is reaching one state, capital A, and so starting state it is reaching the capital A. And for this one, B, A already there and B is there. So here, and we need to write S tends to, and here, so here we are starting with A and we will take starts with B. So S which tends to B, and here we need to write A. So it is reaching for both from the start state. So in start state, when we reach A or B, it is reaching the one state A. And now we will convert, and now we have to take the value. So, and next either it is ends with A or B. We need to check that one. So when it is reaching this state, so this one, if A tends to A, so it is satisfying this condition. and A tends to B, that is satisfying this condition. So here A tends to A or A tends to B. So this is how we have to satisfy all this regular expression. And this is how we are going to convert the regular expression into a regular grammar. And these are the regular grammar for this regular expression. And now we will convert this to a regular finite automata. So for finite automata, so for this regular grammar is which is having the V values are all capital letters. So capital letters are S, A, only two variables are there, and next terminal values are A, B. So A comma B, and next V, T, S. S is the starting state and P is these are the production rules. So grammar we have, and now we will convert it to a finite automata. So finite automata which is having, we need to write this first production rules. So here the first production rule A tends to A. So that we need to convert it to a transition. So delta of S comma A input, it is reaching capital A. So for parallelly we will construct the step-by-step process. So here, so S is the start state and we need to convert the to, when we give A as an input, it is reaching the A state. And next take other production B, A. And delta of S comma B input, it is also reaching the same state. So here, so with the B also, it is reaching the A state. And here A tends to A. So delta of A comma A input, it is reaching the state. So here which state we need to represent here? So we have only a single terminal value. We need to write the next state as a final state here. So here from the A state, when we give A as an input, it is reaching the final state, that is QF. And that is final state is represented with the double circle. And here one more terminal is there, B also. So delta of A comma B, which leads to QF. So here also A comma B I will write. So this is how we are going to convert the regular grammar into a finite automata. And this is the grammar, for the given grammar we are converting it to a finite automata. And after this one we will write the grammar. So we will write the finite automata. So how many states are there? We have 3 states. So I will write A, Q, F, and terminals sigma. So this is the Q and sigma is equal to A comma B. And next S is the start state Q naught and F is the QF, and already got 4 values, and delta. So delta is the production rule which is converted into a transition. So this is about the first example. What we are, the input is a regular grammar and we will convert it to a finite automata. And another example. So first we will convert the regular expression to a finite automata. Regular expressions to a regular grammar. So here the A plus B whole star. So what it indicates? So the string it is going to be starts with either A or B, that too multiple times. So here this A plus B, let me elaborate this A plus B whole star. So A plus B whole star which indicates epsilon symbol initially, and either it starts with A or B and it is a combination of AA, BB and so on like that, and also with the AB, BA like that. And here for this one, so this epsilon, so it's when we are starting with the epsilon, when we are having A plus B whole star, the epsilon is also there. So here epsilon A, B. So this entire thing is not an epsilon. So one more ending with A, B, B. So that so A, B, B machine should we need to end with the final state. So here the S which is belongs to, so either it starts with A or either it starts with B, it should be a self. So here S, S. And also, and it is reaching the next state, S tends to. So for this condition, so either it starts with A or B, and next condition, and we need to enter into another state. We need to enter into another state with the A input, so that I am writing B. So and B tends to, so here we already have A and we need B. So for this one we will write B capital C. So C clearly we can represent with the terminal. So here C we can clearly represent with the terminal. So this is how we have converted the regular expression into a regular grammar. And now we will write the grammar first, then write the transition functions. So here V is nothing but S comma B comma C, and terminals are A comma B, and S is the starting symbol and P is the production rules. And now finite automata we have, later we will write. So then first we need to convert the given we will convert this grammar into a, so this production into a transition. So here delta of S comma A input, and it is reaching the state S. So parallelly we will construct the transition diagram. So initial state is S, so that I am writing the state S, and when we give A as an input, it is reaching the same state. And next take another production rule, a transition of transition of S comma B, which tends to, so same state only, so this one, and we will represent with the A comma B. And next, so and also we need to, for this step we finished. So S tends to whatever we give, that is in the self state only, that represents a star. And here S tends to A, B. So here when we give A as an input here, and also it will reaches the state of B. So here B we need to. So if you observe by here, we have the two input values A. So A input, a single input value, but it is reaching the two states. So this represents NFE. So this represents NFE. So now we are constructing the given grammar into a NFE, finite automata, with a non-deterministic finite automata. And here, and after this one, B tends to BC. So if you give from the B state, if you give B as an input, it is reaching the C state. And here we have the value C tends to B. So here we will write first B comma B input, it is reaching the state. And this one C comma B input, it is reaching the QF. So here we need to write the one more state QF, that is nothing but when we see this terminal, so only single terminal, if we observe single terminal value, so that says that it is reaching the final state. So here A, B, B. And here now we will write this entire thing into a definition of finite automata. So finite automata which is having the Q values, so Q we have 4 states we need to write, S comma B comma C comma and QF is the final state. And the terminals AB, so the alphabets AB, and initial state is S and final state is QF, and delta is the transition. So these are the production regular expressions. So how we are going to convert it into a regular grammar, and then we just convert it into a finite automata, that is also a non-deterministic finite automata. And next example, so here we will take the regular expression A star, B star, C star. So here A star, B star, C star. So here either it having the multiple A's or multiple B's, or A's followed by B's or B's followed by C's. So these are all the things we need to write this regular expression into a regular grammar first. So here S tends to AS. That says that A multiple times of S. So when we write simply, so S, if you give A as an input, it is reaching the multiple times it is A is repeated. And for B also, we will write B S. And for B input also. And for C also, we will write C S and C also. So this entire thing is represented like this. And next CS, and like this. So this is the single thing. So single A star, only B star, like that. But now it is followed by, so that we need to enter into another state, that is capital B. So here the capital B, so when we have a B as an input here, so B as an input here, we need to enter into a next state. So that represents, so it is a 3 length or 2 length, whatever it is, we need to represent it there another. So the one more concatenation operation is there. So we need to more states to represent this concatenation. So B, when we give B as an input symbol, it is reaching the state B. And when we having the input symbol C, we need to represent with the another state. We need to enter into another state. And next also, so this entire A star and B star and C star, so this having the, so in this thing, epsilon will take, in this thing also epsilon will take, and in this thing also epsilon will take as an input string. So this concatenation will also get the epsilon. So that represent the S tends to, so S, which is starting state, so itself it is having the input symbol epsilon. So that says that it is in the final state. And S tends to epsilon. And next B. So after reaching this one state B, we need to give the two input values here. So here after A, we have the two input values B, C. So for first B input and C input. So for the B input, we have a capital B. We need to be in the same state. And for C input, we need to represent with the C. And we already have, and B epsilon is also included. And C tends to, with the input symbol C, and we need to be in the self state. And C tends to, epsilon is also included. So these are the production rules which we are for the regular expression A star, B star, C star. And now we will convert this into a regular finite automata. So finite automata. So first we will write the grammar, then we will write the production rules. S, B, C, and next this is V, and terminals are A, B, C. These are the terminals, and S is the starting state and P is the production rule. And next we need to convert that every production rule into a transition function. So transition function, so we will write every production rule and then we will convert it into a transition function. So first one is this one, production rule and transition. So production rule will take S tends to AS. So transition S, A as an input, it is reaching the S state. The parallel we will construct the transition diagram. So S state we are taking as an initial state, and will we give A as an input, it is reaching the same state. And we'll take another step, another production rule. S tends to B, capital B. So delta of S comma B, so which is in the next state, that is B. So with the input symbol B, it is reaching the another state, capital B. And from this next, S tends to C, capital C, delta of S comma C as an input, it is reaching the capital C. So here if you observe, if you view C as an input, it is reaching the state capital C. And also this S tends to epsilon, that says that, so S comma epsilon symbol, it is reaching the same state. So here same state, that is represented as a final state. And next, B tends to B, capital B. So B, delta of B comma input symbol B, which represent B. So B with the input symbol B, it is reaching the final same state. And B tends to C, capital C. So delta of B comma, so C as an input, it is reaching the C state. So B, it is reaching the C state here. So C as an input here, it is reaching the C state. And B tends to epsilon, so which is B comma input symbol epsilon, it is reaching the B state. So that is represented with the double circle. And next we need to take C tends to C, capital C. So delta of C comma capital C, small c, which leads to the same state, that is nothing but C with the input symbol C, it is reaching the same state. And C tends to epsilon, delta of C comma epsilon, which is reaching the capital C, that represent it is a final state. So this is how we are going to convert this regular expression to a finite automata. So first we need to write every production rule, then we need to convert it to a transition function, and then we need to parallelly construct the transition diagram. This is the conversion of regular grammar into a finite automata. And we'll see the equivalence. So here we just converted into a regular grammar to a finite automata. Now we will take input as a finite automata and we will convert it to a regular grammar. How it is, we will see. We have a procedure like begin the process from the start state. So here we need to begin from here. So start state, whatever it is, in the transition diagram, and write the productions as the output followed by the state on which the transition is going. So here how we need to write? So as same, the reverse process. So here the delta of A comma input symbol A, it is reaching the B state. So here this entire thing will be written as a production rule like, so A tends to A capital B. Like that we need to write the production rule. And also we have transition of, it is reaching the final state. So here from the B comma A as an input symbol, it is reaching A with the capital B, and the transition of A comma B, so B comma B, and B which is reaching the capital B, and also the terminal, so B comma B, which is representing, so B which is having epsilon symbol as an input, and it is reaching the B state. So then we need to convert this into a production rule. So here B tends to A B, and here B tends to B, capital B, and B tends to epsilon. So here B tends to epsilon is included. So here entire we will write the production rule as A tends to AB and B tends to, we have two options, either it start with A or starts with B, and also we have the epsilon symbol. So here when we represent the double circle, one state as a double circle, so final state which is having the epsilon symbol. So here that's why add sigma epsilon symbol, because that is required to end the derivation. So here the derivation is ended with the epsilon symbol. This is how we are going to convert the finite automata into a regular grammar. And we will take one more example. So here this example, which is, if you clearly observe, we have the two final states. So two final states we have, and how many? 1, 2, 3, 4, 5 states are there. So if you observe, after reaching the final state, we have additionally two states. So here these two states are also not leading to the another state, so that it is a dead state. So these two states we need to minimize first. So this minimization, which is after dead final state reaching, we need to remove these states, and we need to construct the regular grammar for the given finite automata. And first we will write a finite automata. So that is, so Q naught comma Q1 comma and Q2. We have three states. After removing these two states, we have a two states here, and we have the input symbols like A comma B, and only A comma B we have. These are the Q comma sigma comma, and Q naught is the initial state and Q initial state, and final states are Q naught comma Q2, initial state and final state. And what we have, delta we need to write. So after seeing this one, so first we will write the transitions, then we will convert into a productions. So transition, first initially we have delta of Q naught comma A as an input symbol. It is reaching the state Q naught. So this transition will be represented as a production rule like, so Q naught tends to A Q naught, and next a transition of Q naught comma B as an input, it is reaching Q1. So Q naught B with the B input symbol, it is reaching the Q1 state. And next delta of, we already finished the Q naught AB values, and we will move to the Q1 state. Q1 comma A as an input symbol, it is reaching the Q1 state. So here Q1 tends to A Q1, and also the delta of, so A Q1 comma A as an input symbol, it is reaching the Q2 state. So Q1 comma A tends to Q2, and also this transition of Q2 with the A input symbol, it is reaching the Q2, and this one is written as Q2 tends to A Q2. And one more, it is a final state. Last we will write a Q2B as an input symbol, it is reaching the Q1 state. So Q2 tends to B Q1. And also we have the final states here like A tends to Q naught and Q2 are the final states. So we will write these final states as delta of Q naught comma epsilon symbol, it is reaching the Q naught, so that it is writing Q naught tends to epsilon, and delta of Q2 comma epsilon, it is reaching the Q2 state, that represents Q2 tends to epsilon. So the entire thing we will write it as a production rule here. Let me write the Q naught as a S, and Q1 as a and Q2 as a B. So here write S tends to A S, and next S tends to B A, and A tends to A A, and so here later we will summarize. And here A tends to this production rule A B, and next also we have, and we have the Q naught tends, so B tends to A B, and B tends to B A. So here, and S tends to epsilon and B tends to epsilon. So after summarizing all the production rules, we will write. So S tends to AS, BA, and also we have the equation epsilon. And coming to the A production rule, A capital A and A capital B. Yes, that's it. And next capital B, and B tends to, we have three equations, so that I'll write AB, BA, and also we have the epsilon symbol. So this is how we are going to convert the given finite automata into a regular grammar. So these are all the production rules what we have written for the finite automata. So this is about the conversion of a given finite automata into a regular grammar. So these are all the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.